Hi, all. So today we are going to discuss about the paper ShardFS and IndexFS. It is a replication versus caching strategies for distributed metadata management in cloud storage systems. Okay, the authors are Lindsay, Kairan, Quinzing, Garth Exhibition, and presented by Abdul Latif Muzaffar Mukram and Alex bin Khanam. Okay, we will go. So introduction. So in today's modern world, there is a plenty of discussion about the cloud storage, and we also learn more about the cloud storage facilities. But main important thing for cloud storage is the index for it or the metadata. So the central problem discussed in the paper revolves around managing distributed metadata in cloud storage system efficiently. In cloud storage, metadata like file names, directory structures, permissions, etc. is a crucial as the data itself, since it enables the organization and retrieval of the stored data. Importance of this problem. So mainly we are going to discuss about how the large amount of data being retrieved very fastly, and so that's how the cloud storage system works, right? So that's why we benefit cloud storage also. So the importance problem of that is scalability of metadata management. As the volume of data in the cloud storage increases, so does the amount of metadata. So that meaning, how much ever the data grows, the number of metadata is also getting increased. So managing this metadata efficiently is crucial to system performance. A bottleneck in traditional approaches. So traditional metadata management systems that rely on a single node metadata service can become a bottleneck. So if you store all the metadata in a single node, it's going to be a problem. You have the data spread wise replicas you have for the data. You will access, so your main data is replicated and it is distributed. But if your metadata is being clustered to a single node, it's going to cause delay, and it's going to cause more overhead for a particular node. So we are going to discuss more about that. Performance hindrance. So yeah, that's why I said, right. So the performance will affect the metadata performance, will also affect the pulling and retrieving of the main data. And large scale data distribution. So this also affects how storage distributed data across multiple nodes and geographies. The distribution poses a challenge for traditional metadata management approaches that were not designed with such a scale in mind. So demand for high availability and reliability. Cloud storage systems are expected to be highly available and reliable, which requires metadata to be efficiently managed to ensure data is always accessible when needed. Need for improved methods. To address these challenges, new methods that can distribute the workload and scale with the system are necessary. This includes strategies for partitioning, caching, and replication of metadata. So we discussed more about metadata. So what is distributed metadata management? So distributed metadata management refers to the systems and methods used to handle metadata information about data across multiple computing resources or nodes in a distributed system, such as distributed file system or distributed database. So here, if you see, for example, these are the clients which are requesting the data from storage devices, which are all are distributed. So what clients will do is, for any read or write operation, they will directly go to the metadata servers. So here you have a distributed metadata servers. From this metadata servers, they will get the address or file path for that particular data what they are looking for, and they will directly access the storage devices. So since if this their metadata servers are distributed, then they don't need to worry about bottlenecks or overhead much for particular servers. So what is namespace? So the important aspect which we deal with this metadata is the namespace. So namespace is the directory structure within a file system. So it's way of organizing and providing a hierarchical grouping for files and directories. In distributed file system, the namespace is what allows the system to locate where files are stored across various servers or nodes within the network. So for example, if we say files C colon and slash and whatever web drive or the C drive we are storing, right? So these values are getting stored in some part of the server. So that is where it's called namespace. So overview. So there are many solutions for this, but we are in this paper we are mainly going to discuss the three things in this metadata management. So there are several solutions that have been proposed and implemented to tackle the problem of distributed metadata management in cloud storage system. The paper specifically mentions and evaluates solutions of the following three file systems. So IndexFS, which is also known as client-side caching, and Giraffe table partition namespace is also called, and ShardFS server-side replication it's also called. So dynamically partition namespace. So what do you mean by dynamically partition namespace? So dynamically partition namespace will come here. So basically, if you see here, these are all directories which are red diamonds. Okay. So in these diamonds, so it will these diamonds which is pointing to the next diamond, it's called the subdirectories. So if you take this is the main row, then below ones are the subdirectories inside it. Okay, so here in IndexFS, the directories are dynamically partitioned. So that means the first directory will be in one server, and the second directory will be in different servers or different nodes, or partitioned different partitioned uh, mount point. So these are dynamically partitioned. So dynamic namespace partitioning in IndexFS introduces a dynamically partitioned namespace, which means that it doesn't statistically assign directories to metadata servers. Instead, it adapts the file system grows. Okay. Upon creation, each directory is assigned to a metadata server at random. So I said earlier, right? So each metadata servers are assigned as a randomly. Okay. But within that directory, if there are any files, that will be organized within that metadata. Okay. So if you see 2 and 3 for under this directory, it is in the same partition one point. So it's also same like the server. So each file, with whatever files are there within a particular directory, those will be there inside the uh, same server. So IndexFS distributes its namespace on a per directory partition basis. Okay. So path resolution is conducted at clients with a consistent lease-based directory lookup caching. So the main thing again, another one main thing which we are looking at is it's lease-based directory lookup cache. Okay, so what this IndexFS does is whenever there are a client, it will directly store the this data structure tree in the uh, client side. So whenever if any updates are happen, so how it will reflect? It will be mostly based on this lease based directory. Okay, so for each directory they will provide a lease. So once that lease expires, only they will be able to update it. So then capability for directory size. It uses a strategy that works well for small directories by keeping related directory entries on the same server. So as I said earlier, the same files which are will be there in the same server, so thereby maintaining operation efficiency. For large directories, IndexFS employs the GIGA plus binary splitting technique. Okay, so this technique distributes the directories entries over multiple servers by splitting the directories hash range as it goes. So this name for files which are being under the same server will be under a one particular server, right? So if that server is occupied with the big huge files, that server might not able to accompany the incoming growth of the huge files. So that time what it will happen is it will split this file data to the next server once this server is fully occupied. Okay, so that time it will use this directory's hash range as it goes. So it will give a directory a hash name, and with that hash name it will move it to the next servers. So this system incrementally splits directories, hash ranges, starting with a full range on one server and dividing it as the directory expands, eventually involving all metadata servers. So it will always include all the metadata servers also. So lease-based metadata caching. To optimize the for POSIX semantics, IndexFS catches directory entries. It uses a lease mechanism where changes to metadata are delayed until the relevant lease expire, reducing the frequency of metadata invalidation. So as I said earlier, this client side it will store the directory structure, and once the lease expires, then only they will be able to change the directory structures or forms. So table partition namespace. So next we are moving to table partition namespace. It's called Zirafa. So what is table partition namespace? It's like we are directly storing that directory structure inside a table. It's pretty much same. Okay. So metadata storage in HBase. So Jirafa stores file system metadata within a distributed table in HBase, which provides single row transaction guarantees. Each file in the Jirafa namespace is stored as one row in the HBase table. So each directory will be stored as a particular row in the HBase. So these, if you see here, these are the HBase entries you can see. Slash A slash C slash 2, it's stored in this particular directory, particular row. Okay. So hierarchical namespace management. To maintain the hierarchical structure of the file system, Jirafa embeds the file system tree structure within the row keys of the file system objects. So if for hierarchical structure, they will store the row keys of the file system objects within the. Okay. So the default strategy for row keys includes using the full path name prefixed with the depth of the file system objects. So each path name will be prefixed with the depth of the full system. So you will get the full path here for a particular row. So it doesn't need to go back and go back forth and check the full path name. Implementation details is implemented as a co-processor within each HBase region server. The system depends on the underlying HBase to dynamically partition and distribute the metadata table across all its region servers to achieve load balance. HBase partitions its table horizontally based on a fixed region size. However, it does not understand the semantic meaning of the stored contents. So it does not partition directories into index like IndexFS. So this does not partition the directories. It will just directly store the uh, values here. So it doesn't need to partition across multiple regions. So we have considered two distributed metadata management systems. So that is IndexFX and Zerafa. So we are going to look at the limitations of those existing systems. So scalability issues. While client-side caching can reduce the load on the metadata server by catching metadata on the client side. So this might pretty seem like a useful way, but it faces a challenges in scaling as the number of clients increases. So when the number of clients increases, managing those all cache is a pretty much problematic, as you need to update all the cache servers once the any changes goes into the metadata. So consistency concerns. Ensuring consistency of metadata across multiple clients can become a complex and resource intensive. So that's why I said, right. So you will have multiple RPCs, remote procedure calls, for updating each and everything in the of each and everything of the metadata for every client cache, right. So that is a pretty much uh, time consuming and overload for all the servers and nodes. So pretty much your network and bandwidth, everything will go for that. So that is also a big problem in the IndexFS. So Jirafa table partition namespace. So limited flexibility only we will be having for Jirafa. Solutions like Jirafa which use a table partition namespace may not be flexible in handling diverse metadata operations. It is very difficult to handle diverse metadata operations. So bottleneck for this is these systems can still face bottlenecks, especially under high metadata operation loads, impacting overall system performance. The row key schema used by Giraffe also affects directory rename options. So the main problem we have is, so for each and every directory within the HBase, we are giving the full path name, right? So if we are renaming any of the source or main path names, so if we are having thousands of rows within that main directory, so we need to go and change the thousand um, rows also. So that is becoming a big problem. Okay. So because of the difficulty of supporting atomic rename for directories, Jirafa currently only supports rename of files in the same directory. So due to this huge update is needed for this operation, HBase only supports renaming of the files. It doesn't support the renaming of the directories, because whenever you do a small change, if it is having 1,000 directories inside, subdirectories inside that main directory, the 1,000 rows are going to get changed. And if you are having any files within that, so those files also will be get changed. So if it is you are having 10,000 files in that, so the 10,000 files also will get changed, and 1,000 directories also will get changed. So it is going to be a hectic problem works. So the proposed solutions. So after this, seeing these limitations, right? So there is a better approach which we can work on, and those approaches are the one. We call it as a ShardFS, which are replicated directories with shard files. So replication of directory lookup state. ShardFS enhances the performance of distributed file system by fully replicating directory lookup state across all servers. So I will show you here. So if you see these are consider these four as also servers. So the tree structure is the same. Okay, the directory structure is the same. Okay, but if you see this red color and black color, it might pretty much seem like a red black tree, but I will tell you what it is. So this red color square diamond are the ones where the directory currently resides. So this red color meaning the directory is currently in this server. So here, if this node is indicating as a red color, that means this directory is there in this server. So whichever it is a black, it is just replicated from the metadata servers. Okay. So this is very simple, right? So you will get a whole structure, but the particular structure is being residing on the particular server. So this is being achieved with the help of the hash key value. So they will use this hash to get that particular directory being attached to that server. So this is very useful. So if you make any directories changes, that changes will reside within that locally of that server, and it will get replicated to the all other states. So servers for the path name, such replication slows down mutations affecting this information, like changes to the directory names, direct access permission, or namespace parent child structure. Local path resolution. Every metadata server in ShardFS contains a complete replica of the namespace information, allowing path resolution to be performed locally. So if you see here, if there is any change within this, in the locally change, it will be completed easily. This means that a single remote procedure call to appropriate server is sufficient to complete path name resolution. So each any single RPC is enough to get. So whenever you are here to resolve the path, you can directly go from this server to you can get the uh, path name. So this is very easy. So sharding of file metadata. Unlike namespace tree structures, file metadata in ShardFS is stored on only one metadata server. File metadata is distributed using a sharding function based on the path name, with each path name being assigned to a primary metadata server. Concurrency control. ShardFS is based on pessimistic multi-server looking for all metadata operations. However, operations accessing metadata on only one metadata server can execute with a single RPCs, making them internally serializable and transactionable. For single RPC operations, ShardFS employs optimistic concurrency control and falls back to two-phase locking when optimistic verification fails. So here we have seeing about optimistic concurrency control, right? So optimistic concurrency control, what it means is, so if you're making any change for this file, okay, and I am making the same change in the different file, okay, but this won't get lock the file, particular file while changing it. Okay, it will log only during saving. Okay, so if we face any issues during saving, like it's not matching and it is the persons are not same, like that issue if you are occurring during saving, then it will go fall back bit before two-phase locking, and it will lock, then you will be able to make changes. So this is called optimistic changing. So then we are going to compare these three systems. So this will give you an overall picture of it. So shared files are called replicated directory lookup state, where shared files, um, then IndexFS, it's more pretty much the partition into directory subsets, right? So and then this Giraffe is getting stored partition by the HBase. So based on the HBase, it's getting stored the data. So hashing of the path name is being here used, and in IndexFS, parent directory inode num plus hash file name is getting it's being used. So here, if you see in Giraffe, the full path name plus depth plus path name is being used. File operations. So file operations, we have many operations. So in that many operations, one RPC call is being used for shared files, and many RPCs are being used for cache, because you have to go front and back to each and every server in the client. So um, Giraffe, we will use one RPC for stat and change mode, and two RPCs for make node. But we won't be changing the directories here, because it's not possible here. So that's why we are having it here. And we have directly metadata mutations. We optimize monotonic distributed transactions. As I said earlier, one RPC that waits for lease expiration here. So whenever the lease completes only, we will be able to provide the next changes. So concurrency control, optimistic single RPC is, we mostly will try to complete this shared files with a but single RPCs. So that's the best advantage here in shared files. So whenever you're doing any changes in the IndexFS, you need to locking at the directory partition level, and then you need to make any changes here. So client catching, only cache configuration info is getting cached here in ShardFS, but in namespace you will get whole structure being cached. So that's why we call it as a client catching. So catching path, prefix, ACLs, and directory partition locations. Cache the location of the tablets. That's all. So load balance file access by hashing. So these are the ones how the hashing being worked on the and, partitions are being getting used. Yeah. So we will continue this from Abdul.
Yeah. So, hello, I'm Abdul, and I'll be proceeding with the implementation and results. Uh, here, uh, Here we'll discuss the methodologies used for the experiment. The researchers adopted three approaches for that. The first one is micro benchmark. The second one is trace, replay, and scaling experiment, and the third one is weak scaling workload experiment. In the micro benchmark, the first one, this involved a detailed examination of performance using balanced Zipfian and synthetic trees to stimulate various directory structures. The evaluation included metrics such as average throughput per server, RPC amplification, and load variance. Mm, Now we'll look at the implementations and results of the first one, micro benchmark. Here, different tree structures were employed to assess system performance. This included balanced trees, Zipfian trees, and synthetic trees generated from Yahoo cluster trace. Performance measure encompassed average throughput per server, RPC amplification, and load variance. Now we'll look at the performance measures. The researchers evaluated key metrics such as average throughput per server, RPC amplification, and load variance. Moving on to the evaluation based on the micro benchmark results, ShardFS showcase efficient directory sharding, maximizing insertion throughput. IndexFX demonstrated incremental partitioning but could encounter challenges with smaller directories. Giraffe showed a tendency to avoid splitting directories, potentially leading to load imbalances. Now we'll look into the second methodology, that is trace, replay, and scaling experiment. Here, the performance of IndexFX and ShardFS was compared using traces from a LinkedIn cluster. Now we'll look into the evaluation of this methodology. The evaluation based on the trace, replay, and scaling experiment shed light on the challenges faced by both IndexFX and ShardFX. IndexFS encountered issues with cache effectiveness, potentially leading to bottlenecks, while ShardFS grappled with increasing overhead in directory lookup state mutation operations. Now we'll look into the third methodology, which is weak scaling workload experiment. Emphasizing scalability as the system size grows. we'll look into the evaluation of this methodology. In the final stretch of the evaluation, the weak scaling workload experiment revealed that IndexFS experienced a slowdown in performance as the number of servers increased. In contrast, ShardFS maintained better scalability, particularly when the frequency of metadata updates remained constant. Now we'll look into the summary. We can summarize that cloud storage lacks efficient metadata services. The paper identifies key design trade-offs and introduces ShardFS, a system tailored for weak scaling metadata workloads. ShardFS achieves higher throughput through directory lookup state replication. Experiments compared ShardFS metadata operation performance with alternative designs. IndexFS relies on cache locality for storing scaling, while Giraffa sacrifices file system semantics for reduced network round trips. ShardFX excels in weak scaling and read intensive scenarios, demonstrating superiority in linear scaling and lower response time. Now we'll conclude. Uh, the the author manages to show that ShardFS provides better performance under weak scaling and read intensive metadata workloads. The paper appears to be well structured with a clear layout that introduces the problem, explores existing solutions, and presents the proposed ShardFS followed by a systematic comparison and conclusion. The paper offers insight into the challenges faced in cloud storage metadata services, the limitations of existing systems, and potential solution, that is ShardFS, to address these challenges. It's essential to critically analyze the proposed solution, particularly its applicability in various scenarios and potential drawbacks not extensively covered in the paper. Overall, the paper appears to be comprehensive and well researched. It identifies crucial gaps in cloud storage systems, metadata services, and provides a novel solution, that is ShardFS, with evidence of its potential advantages over existing solutions. And that's it. Thank you. I hope you like our presentation.